Okay, so our first example here is going to be a function from any ring to itself, and we're going to define it. So, once you say what the domain and codomain is, you then have to say what the rule for the function is. And the rule is when I plug in an element of my ring, I get that same element back. So this function is often not denoted phi. In fact, I'm not going to write phi here. I'm going to give myself a little bit more space and say this is the identity function on the ring R. And it's defined by the rule that when we insert x into the identity function, it spits out x. And we're just subscripting it with an R to indicate it's the identity function from R. Great. So let's check that identity is a homomorphism. So I claim the identity is a homomorphism. Now, morally, what's happening is homomorphisms are the functions that preserve structure. The identity preserves absolutely everything. It is the identity. It's the thing that changes nothing. So if the identity doesn't preserve structure, all is lost. All right, but let's check it. So we need to check that it preserves addition. So the identity on x plus y, we want to know, is that equal to the identity of x plus the identity of y, or on y, however you want to say it. And so again, we can't just write this down. We want to know, is that true? So we're going to compute the left and right hand sides, and we're going to see what we get. On the left hand side, the identity just spits out whatever you plug in. So the left hand side is just x plus y. And also, the identity just spits out what you plug in. So it's going to spit out x for this first guy and y for the second. So are they equal? Yeah, they're equal. Gold check mark. Then we're going to ask, does it preserve times? So is it true that the identity of x times y is equal to the identity of x times the identity on y? Oops, that's supposed to be a times. And so this is a question. We have to compute both sides and check and see if they're the same. Well, the identity spits out whatever you plug in. So the left-hand side is x times y, and the right-hand side is x times y. So are they equal? Yeah, they're equal. Fantastic. And now we have to check the last condition, that it preserves unity. Well, is the identity of 1 equal to 1? Well, yeah, it doesn't, of course. That's what identity does to 1. So is the identity a homomorphism? Yes. So we conclude from this that the identity is a homomorphism always. It doesn't matter what ring it is. It's just always a homomorphism. In fact, it's not hard to convince yourself that the identity is both 1 to 1. It doesn't collapse anything. And onto. Every element of the codomain comes from something in the domain, namely itself. So this tells us then that because it's 1 to 1, the identity is a monomorphism. And because it's onto, the identity is also an epimorphism. So we're both a monomorphism and an epimorphism. So this tells us that the identity is an isomorphism. That's the criteria for being an isomorphism. You're monic and epic. But the codomain and the range are the same thing, right? They're both R. So the codomain and the domain are the same thing. They're both R. So this tells us the identity is an isomorphism from the ring to itself. So it's an automorphism. It's all of those things, actually. Not all homomorphisms are all of those things. They're usually none of them. But in fact, it is all of the orphisms that we've said. To be a monomorphism or epimorphism, you first have to be a homomorphism, and then you have to satisfy extra stuff. To be an isomorphism, you have to be both a monomorphism and an epimorphism. And to be an automorphism, you have to be an isomorphism, which has the same codomain as the domain. So anyways, this actually satisfies all of those definitions. And just to be clear here, what we're learning that you should use again and again, let me write it in blue, is automorphism implies isomorphism, implies monomorphism and epimorphism. Implies homomorphism. So what would be the best orphism to describe the identity? The best is sort of the strictest one. And so we would say, in this case, the identity is an automorphism, because when you say that, it implies all of these other ones. All right, let's do a less trivial example. We're going to look at the function, I'll call it phi, from a general ring to itself, defined by. So again, once you say what the domain and the codomain is, you then have to say what the rule for the function is. And phi is going to be take the additive inverse function. The additive inverse, we proved a while ago that the additive inverse of every element is unique. So the additive inverses are unique. That is, an element can't have two different additive inverses. Phi is well defined. That is, you're never going to plug in an element of your ring and get more than one output. You only get the one output, the additive inverse. So let's check the properties and let's see if phi is a homomorphism. So let's see if it preserves addition. So we need to compute phi of x plus y, and we need to compare that to phi of x plus phi of y. I'm going to put a question mark through this because we don't know if that's true. So phi is take the additive inverse, take the additive inverse, take the additive inverse. Now, negation distributes over addition, so this is negative x minus y, because negation is multiplication by negative 1. That's another way of thinking about it. So is it the case that it preserves addition? Yeah, it does. Great. Let's look at what happens for multiplication. So we need to check, is it true that phi of x times y is equal to phi of x times phi of y? Again, I'll put my yellow question or orange question mark because I'm not sure. So phi is the I negate whatever I plug in function. So we're going to plug in xy, so we negate xy. And then we're going to negate x for this guy, and then for the next one we negate y. So we're asking, is this true? Well, negative x, negative y is positive xy. So we have to ask, is that true? And the answer is, it depends. So it depends on what ring we're in, right? We never specified the ring up here. So this is true sometimes. It's true in particular when you have what's called a Boolean ring, where negative 1 and positive 1 are the same thing. So it's true sometimes, namely, I didn't say this correctly, namely when negative 1 and 1 are the same. So what are examples of such a ring where that would be true? Well, we saw f2, 1 and negative 1 are the same, and we can look at polynomials over f2. And we actually saw this other thing, f2 squared, in class, where 1 and negative 1 happen to be the same thing. But my point here is not that go look at these, certainly. My point here is that there's no contradiction here yet. We have a contradiction in general, but there's some cases where this is true. In general, it's false, but sometimes this is true. So does it preserve times? Well, only when -1 and 1 are the same thing. And let's check preserve unity. So phi of 1 needs to be 1, and that's a question now. What does phi do? It negates. So -1 needs to be equal to 1. So this is true in the same instances where it preserves times. So phi is only, so what's our conclusion from this? Phi is only a homomorphism if R is a ring where 1 equals -1. Otherwise, phi is not a homomorphism. It fails to preserve both multiplication and the unity. Great. Now, in the case where phi is a homomorphism, so 1 is -1, phi, it's not hard to convince yourself, is actually a monomorphism because phi, well, how do you show that it's a monomorphism? Suppose, well, let me actually not go down that route. Let me just notice here, if 1 equals -1, then phi is -1 times x, but 1 and -1 are the same. So phi of x is just x. So phi of x equals -x, but 1 and -1 are the same thing. So phi is the identity, right, in the case where 1 equals -1. So phi is actually an automorphism because it becomes the identity map in this case. So the answer to this question is in general no, but sometimes. All right, in the next video we'll do a couple more examples.